Hello and welcome back. In the previous video we assembled and completed the front panel board of the SCELBI 8B, as you can see here, and we inserted it into the computer. And in this video we'll be assembling the next board, which is the CPU board, and I think this is the more I guess the most complicated board of the set. Not only does it have a lot of components, but also is a bit complicated in that there are a lot of moving components, I guess moving parts inside the board itself. And it also has the 008 microprocessor that goes on here, which is the brains of the computer, I guess, and all the remaining components are the supporting functionality of the microcontroller. One thing about this board, and the reason why it might be the more complicated one, is that once we assemble all the parts on this board, we'll actually have to tune it so that the clock is correct. Basically, we're going to create the clock for the microcontroller, and it has to be at 500 kilohertz, if I'm not mistaken. But there's a two-phase clock, so phase 2 will be sort of like the off phase 1, so it'll be shifted a little bit. And to do that, we'll need some tools. And I think if you have like a good oscilloscope that can actually show you the waveform and also the frequency, you can probably tune it with that kind of a oscilloscope. The manual, the original manual, actually calls for an oscilloscope to kind of see the waveform. And I think the assumption was that you would have an oscilloscope that you could see the waveform, and you would kind of be able to see where each wave starts and ends and things like that. Basically, check the time between each wave, I guess, rise and fall and so on. But it also calls for a frequency counter, and I guess it was to actually count the frequency of each wave. My assumption was that maybe the older oscilloscopes just didn't have that functionality where you can actually get the frequency of a wave. A lot of the modern oscilloscopes actually have that functionality. You can actually calculate the frequency of a wave. So you will need an oscilloscope for this board to tune it. I have one actually right in front of me, so I'll be using that. So let's take a look at the manual. So as before, we'll start with this page here where it describes the 1100 card, which is the CPU card, and it just kind of goes into a little detail on how the CPU board actually works. I guess it's called a card. They call it a card. How the CPU card actually works, and the clock and things like that. And it also mentions about basically adjusting the clock and what I just mentioned about using an oscilloscope and a frequency counter. There's a page 2 to it, and it's the layout. I'm going to actually take this out of the binder while we assemble it, just so I know where each component goes. And of course, it has the assembly instructions for all the components. We'll sort of follow it as usual. We might diverge a little bit by installing lower components first. And then it actually has some inspection and testing instructions just to make sure that the board doesn't actually have any shorts once we finish the assembly of it. And it continues on the next page here, and it has the master clock adjustment instructions for the CPU. So we'll actually reference this once we install all the components on the board. And these instructions actually span a couple of pages, and then it actually ends, I think, on this page right here. Basically, this is the details page. It has all the information on this one page, whatever was mentioned in the previous pages. It's all in here. So you can actually reference this page when you adjust the clock. Now we can jump all the way to this other page here. Basically, the last few pages of the manual contains the schematics and some additional details about each board, so we can jump to that. And as you can see, there's a lot of information here between that. I don't know why it was done like this. Could have just included it all in one location. But basically, this page right here, it has the power requirements for the board, the CPU board, and just kind of shows you how it works in general. And of course it has a schematic here. It's probably the most complicated schematic here. And by the way, I actually had to reference this schematic when I made this board. I actually converted this schematic into KiCad, just created them by hand, and then I created a PCB using that schematic. I laid out all the components the same way that the original was laid out, and then I drew the traces the same way. And the way I actually verified that I was actually correct is by using the schematic. So this is actually based on the schematic. And the last page here, actually 2 pages, it contains the parts list. I actually already got all the parts right here, all the ICs, and of course I'm going to use these IC sockets that we used in the previous video. Some capacitors, and a couple of diodes, and resistors, and I have these trim pots for adjusting the clock. Okay, I think we are ready to start the assembly. Let me go back all the way to this page right here, and I guess we can start with. It tells us to start with the integrated circuits. We won't be installing the ICs directly. We'll actually install the sockets first, and then we'll insert the ICs into the sockets. But actually I'm going to skip that for now, because the reason why is because these are higher profile than some other components, and we'll just start the installation of the resistors first. I'm going to install this resistor here that's for R34, and there's only one of them. And I actually noticed a discrepancy here. So if we look at the parts list for R34, let me find it here. So right here, it actually says it's a 33K quarter watt resistor. And also the installation instructions also call for a 33K ohm resistor. Orange, orange, orange. But on the parts list, it actually calls for a 30K. And I couldn't actually find a 33K as the parts list had said. But I did find a 30K right here. So I'll actually use the 30K instead of a 33K. I don't know how much of a difference it will make, but I suspect not much. All the resistors and diodes have been installed. I think I'm going to install the IC sockets next, and I guess we can install any other component because it looks like pretty much all of them have similar footprints except for the fuse clips here. But I think I will do the IC sockets in my case. And most of the ICs are actually 14 pin. All these are 14. I think there are there's actually one, I think, that's 16 pin. We want to insert that first. I think it's right here. There's another one that's 18 pin actually, and maybe we should insert that first, but I'll insert the 16 pin one in here first. The 18 pin one, that's for the microprocessor, which by the way is right over here in this foil. I'll use a 16 pin socket in here, and then I'll just insert 2 additional pins by just pulling these out and inserting them directly. So I just gotta remember to do that later, but I'll do that once I solder in all of these, and then I'll just go back and insert 2 more pins into that one. So I'll go ahead and insert the 14 pins into their positions. So I actually was wrong. There are two 16-pin positions, one here and one over here. So I'll just use this one right over here, and I'll just get two additional pins for the 18-pin socket for the microprocessor. I guess the last thing is to install these two pins to make the 18-pin IC socket. So I'll just remove one of these, actually two of these pins from one of the sockets, and just insert it into the hole. And that's pretty much it. Looks pretty straight, but if not, we can just make it straight with our finger. It's actually pretty solid. It's like hard to bend. Okay, we got the ICs installed. The IC sockets installed. We don't need this for now. I can just set it aside. I guess the next thing we can install are the. I guess let's go with the capacitors. Actually, let me go ahead and install the single transistor here, and then we'll do the capacitors. And we'll orient this transistor so that this tab is oriented the same way as is shown here on the drawing. It's a little off screen here. Yeah, so on the drawing we have this tab facing, I guess, bottom right. So we'll face ours bottom right. And based on the instructions, it actually says to insert something underneath the transistor to add some spacing between the transistor and the PCB, about 1/8 of an inch. And it says to use a matchstick. I'm actually going to use a piece of wire here that I had laying around, and I'll just slide it in here so that it stays in here while I flip it over. And we'll just push it down and apply some tape to keep it in that position while we flip it over and solder it in. Alright, let's go ahead and install the electrolytic capacitors. There are 3 10 microfarads. These are rated at 25 volts. So let me go ahead and install them. I think we have one right here, and one right here. And each one has a plus sign. Actually, not each one, actually a single one. Only this one has a plus sign where the plus goes, but I guess for the other ones we have to reference the layout sheet right here. But it looks like each plus sign is actually facing upwards, well, away from us when the board is oriented this way. So let's go ahead and install them. I'll install the fuse clips next, and we'll install them with the fuses directly. I'm just going to install a random fuse for the time being and just remove it later. Also, there is a specific orientation for these fuses. As you can see, there are edges on each one, so we just want to make sure that we use or orient them the right way. I just removed the fuses just so we can install the correct ones later and not forget about it. We also need to install these trim pots. I think we can go ahead and install them now. And these are all the same values, so it doesn't matter which one we install where. And as I mentioned earlier, these will be used to adjust the clock for the processor. And finally, the capacitors. I think there are 3 different values. There's one 0.2. There are like 6, 7, 0.1s, and also 330 ohm. I'm going to install the 330 ohm first, and let's reference the layout here for the locations for each one. It may be confusing which of these paths to use for the components. I think basically if you look at the paths here, there are VS and there's paths, and you might be confused by that, but basically the paths are a little bit larger than the VS. So yeah, we don't want to insert any components into the VS. We can now insert all the ICs into the sockets, except for the 8008 here. We got to do some tests first before we insert it in. So I'm going to go ahead and remove these plates from the IC sockets and insert all the ICs into their positions. Now would be a good time to check to make sure that all the ICs are oriented the right way. And it looks like all of them are actually oriented with pin 1 facing up, so it should be easy to check. And also we want to make sure that none of the pins are actually bent, because that can happen sometimes when inserting ICs. And these sockets are pretty nice at that. We can kind of see between them to see if any pins are bent inside or on the outside here. And it looks like it's pretty good on my side here. Okay. ICs are good. Actually, I really like how the board has turned out. It looks pretty cool. So now that we have all the components installed, let's follow the manual here on the initial inspection and testing. So as it says here, to basically carefully inspect both sides of the board to make sure that we don't have any shorts or anything like that, and make sure that all the components are installed properly, all the pins are soldered in, and also the ICs are oriented the right way, and also don't have any bent pins. And then it tells us to install the 750 milliamp fuse into F1, which will be the F1 I think is the 5 volt side, and F1 is right over here. We'll just clip that in there. And then it says to temporarily jumper this fuse right here, and we're going to run some tests. I think, you could potentially install the fuse in here, but this is a 1/8 amp fuse, and potentially some of these meters that could be used to check for shorts and check resistance might be providing a little bit too much amperage, so that's probably the reason why we're actually shorting it with the wire instead of using the fuse itself. So I'm just gonna go ahead and short it with a piece of wire, just like that. All right, let's use an ohm meter to do some measurements. Okay, so it tells us to measure pins A1 and A3. So we have A1 right here. That's the first pin, and we're gonna measure A1 through A3. So I'm seeing 845 that way and 326 the other way, and it should be greater than 5 ohms. So I think we're good there. Now we can try the A3 and A5. 756. All right, I think we're good there. So I'm gonna go ahead and remove this jumper wire and insert this 1/8. So it's a 1/8 amp fuse into this fuse holder. All right, so I think the board is ready. Now what we can do is start adjusting the master clock. I'm gonna use my oscilloscope here in front of me, But let me go ahead and set it up, and then we'll be back. I have a power supply right here that I got off Amazon at one point. It can basically provide power up to 30 volts. I adjusted it to 5 volts and I hooked it up to the board here. Just be sure to adjust it to 5 volts first before you actually hook it up and turn it on, because you might burn some electronics here if you turn it on and then adjust it. So it's adjusted to 5 volts. It's not on yet. And I connected positive side to A1 and the negative side to common right here, the third pin, which is A3. And then I got my oscilloscope hooked up, and I connected both probes grounds to pin 3, which will be the ground or the common. And one probe is connected to Z8 pin 6. The other is connected to Z17 pin 6. So Z8 pin 6 and Z17 pin 6. This Z8 will be clock phase 1, and Z17 will be the clock phase 2. And now that we have it all hooked up, we can actually start adjusting these potentiometers here to get the right clocks for both phase 1 and phase 2. So I'm going to go ahead and turn on the power supply. I got the oscilloscope on, but let's just see what we're getting so far without any adjustments. Alright, so I'm inputting 5.2 volts into the board. Everything seems okay so far. I am seeing some activity on the oscilloscope. It's showing, so yeah, I'm getting 2 waves, so 2 phases are actually working. That's good. If you're not seeing any activity on the oscilloscope, check to make sure that, number one, everything is set up here correctly and all the ICs are in the right place, right orientation, and the ICs are actually correct. But one other issue that, according to the documentation, that might happen is that the power supply might not be bringing the voltage up to 5 volts quick enough. So try either try a different power supply, or maybe add a little switch that you can just kind of toggle on and off. So now with the oscilloscope on right over there, we will adjust these trim pots using a screwdriver. And we'll adjust this so that the minimum, the low state and the max state of the wave are certain values. We'll start with the phase 1 of the clock. So these first 2 trim pots will be for phase 1, and they control the low and the high lengths of the wave. And we need to make the high length of the wave at 850 nanoseconds, and the low part of the wave be 1150 or 1150 nanoseconds long. So we can adjust these by turning them. Let me go ahead and turn on the power supply and see what we're seeing so far, and then we can adjust it. So on the oscilloscope, I have the phase 1 connected to this yellow probe. So I want to make sure I select that first. So this part right here is now yellow. That means we can actually add and remove things. So for example, if we want to see the width, I guess I was calling it the length, but the width of the positive side, we can select this and actually have it added right there. And the width of the low side, I have it right here. So I added the width of the high side and the low side, and we can see the values here. And we can adjust these trim pots here to get the values to the, well, as close to the values as the manual calls as possible. So right now I'm trying to adjust the high side, and I think the manual calls for 850. So let me adjust it to 850. Okay, so we're about 900. 860. Okay, somewhere around there is 850. And the low side is 1150. And I'm going to adjust the second trim pot for that. So I'm actually at the maximum that the trim pot supports, and we're actually stuck at 1070, 80 or something like that nanoseconds, unfortunately. And the frequency is at 520 or so kilohertz. We want to be at 500 kilohertz. One way that I can actually fix this is by installing or adding an additional capacitor here to the low side, I guess, the low side trim pot right here. I'm going to add this 20 picofarads capacitor in parallel with this 330 picofarads, and that should raise us up to about maybe 1200 or so nanosecond width, and then I can just trim it down a little bit to bring it down to the desired value. So let me go ahead and solder it in. There you go, I just added it in, and honestly I don't know why it's doing that. I would think that 330 picofarads was enough for this, but maybe my capacitor just, you know, it drifted a little bit. Alright, I think that's perfect right there. So we have it at about 1150 nanoseconds width for the low side and 850 nanoseconds for the high side, which is perfect. And the frequency is perfectly at 500. It does drop by maybe 1 or 2 kilohertz, but it's pretty steady at 500. So now that we have the high width and the low width correct for clock phase 1, the yellow wave, set, and also the frequency at 500 kilohertz, we can now adjust the clock phase 2 to make sure that it actually rises at the right time and falls at the right time. And according to the manual, it says that clock phase 2 should rise about 200 nanoseconds after the fall of clock phase 1. So what we're looking at here on the oscilloscope, clock phase 1, the yellow wave is falling, and then clock phase 2 is rising. And we want to make sure that it actually is about 200 nanoseconds in between. Each horizontal line there on the oscilloscope is 200 nanoseconds, as it says right there on the top left corner. So we can actually just use those horizontal lines to adjust that. And to adjust it, we just adjust I think it's R29, the third trim pot. This one right here. So we'll adjust that until the rise of clock phase 2 and the fall of clock phase 1 is approximately 200 nanoseconds. And there, I actually adjusted it. And the way I verify is basically I have it trigger on the fall of clock phase 1, and then I can move the phase a little bit until it's centered, or basically align it with a horizontal line. And we can see that the next horizontal line right over here, the second one over, that's where the rise of clock phase 2 is, and that's about 200 nanoseconds in between. So I think we got that one correct, and now we have to make sure that the high time of clock phase 2 is correct as well. And according to the manual, I think it needs to stay on or high for 550 nanoseconds, and we can use R31 to adjust that. So let me adjust that now. And you can observe clock phase 2, the blue wave, as I adjust it. And I'm adjusting it. Oh, that's going up, so we can go down. And by the way, I selected the positive and the negative widths on the left side, and now it's actually showing it on the bottom right over there, so we can actually see the exact duration of each period. So I'm adjusting it down right now. It's like 600. We need it at 550 approximately. And there we have it, 555, 550. So now we have the clocks set correctly. So as you can see right there on the bottom, you can actually see the width of the high width of the blue wave, and also you can see the low width, but the low width we're not too worried about. We just want to make sure that it actually rises at the right time. And we can also see the clock phase 1, the yellow line, the high width and the low width. and also the frequency, which is about 500 kilohertz. I'm going to adjust this slightly more just to kind of be as accurate as possible, but I think we're pretty close to what it needs to be. I made a couple of small adjustments to get it close to 500 kilohertz as possible, and I think this is my final wave, and I'm going to go with this. If something doesn't work correctly later on, I might go back and readjust it, but I think we're pretty good here. I'm going to go ahead and actually stop it right there just to kind of get the final wave. And that is it right there. I'm going to let it run for about 30 minutes as the manual suggests, just to make sure it doesn't drift anywhere, and readjust it if necessary. I'm also going to apply some maybe some hot glue over the top of the trim pods so they don't actually move by accident. If we compare it to the wave drawn in the manual, I think it's pretty close to what we're seeing. So now that we have the clock phases adjusted, there's one last step before we insert the Intel 808 into the sockets here, and that is to actually jumper positions E1 and E2 right over here on the parts placement. These two pins here, E1, E2. And there's also E3 right here, but we're going to leave it open like that. According to the schematic, this jumper here affects the clock for the CPU. And right now it's actually, if we tie E1 to E2, it will basically send a ground into it, common, so 0 or low. So we'll just kind of use the standard clock. If we actually jumper E1 to E3, it will actually invert the signal, so it'll always be high instead of always being low. And honestly, I'm not exactly sure what these jumpers are used for. Maybe we'll find out later on, but I guess for now we'll just do what the manual says and jumper E1 to E2 and adjust it accordingly later on. My assumption or my guess is that it has something to do with the TTY board, but we'll find out later. So let me go ahead and jumper these two pins here. All right, we got that jumper in. Let's go ahead and insert the 8008 into its socket. And again, this microprocessor is pretty sensitive, so be sure to actually ground yourself when you handle it. Some sort of placeholder. And we want to orient it with pin 1 facing away from us, away from the card edge connectors here. And let's just double check to make sure all the pins are in and none of them are actually bent. Alright, I guess the final step is to actually insert it into the backplane of the SCELBI computer. And we probably won't see much difference from the front panel board that we assembled. The only difference might be is that the lights might change on the front panel, basically the run status stop signal lights that are coming from this board. But I guess we'll see. So let's go ahead and put it in the computer and power it on. Okay, so I got to insert it and the power supply connected. Let's power it on. And it appears to be working. Got the lights on and everything. I don't know if the lights will actually change if we press any of these. Oh, they do. So I just pressed step and it changed. What about run? Interrupt? Yeah, so the lights appear to be working. I guess the CPU is working. Okay, that's good. I hope you enjoyed watching this video, and please click the like button if you found it interesting. Also, don't forget to subscribe if you haven't already. In the next video, we're going to assemble the next board in line here. I'm not sure which one it is, but I guess it'll be a surprise for all of us. But yeah, be sure to subscribe if you haven't already, and I'll see you in the next video.